When you think about clean water, you probably picture something crystal clear, right? But what if I told you that the water coming out of our most advanced treatment plants is hiding an invisible problem? Yeah, a whole new generation of microscopic pollutants is slipping right through, and they're posing risks we're only just starting to wrap our heads around. So today, we're going to dive into a pretty radical solution that uses a kind of supercharged oxygen to hunt down and obliterate these hidden threats.
All right, so here's our game plan. We'll start by uncovering our water's invisible problem. Then we'll look at a solution that's literally inspired by the sky itself, ozone. After that, we'll break down how ozone launches its, well, radical chemical attack, see how scientists are supercharging the whole process, and finally, we'll talk about what this all means for the future of water.
First things first, let's get a really clear picture of the challenge we're up against. You see, our traditional wastewater treatment systems, they were designed for a totally different time, and honestly, they're really struggling to keep up with 21st century pollution.
I mean, we've always kind of put our faith in these systems, right? Dirty water goes in, clean water comes out. Simple. But is that really the full picture anymore? What exactly are these systems missing?
Well, the reality is, a whole host of modern contaminants are just sailing right on through, totally untreated. And we're talking about micropollutants from things like pharmaceuticals and personal care products, lotions and soaps, plus stubborn industrial dyes and chemicals that can mess with our hormonal systems. And maybe the most alarming of all, something called antibiotic resistance genes, or ARGs.
And check this out. This quote from a recent study, it lays out the stakes in a pretty terrifying way. It basically points to this feedback loop where our treatment plants, the very places designed to protect our health, can accidentally become hotspots where bacteria trade resistance genes. This amplifies one of the biggest threats to modern medicine and then releases it right back into the environment. It's a huge problem.
Okay, that's the scary part. We've got a serious problem that needs a seriously advanced solution. So now, let's see how science is fighting back, with a powerful set of tools inspired by one of the most reactive molecules in our own atmosphere.
The answer is in a class of treatments called Advanced Oxidation Processes, or AOPs for short. Now, the main idea behind AOPs is to generate an army of what you could call molecular assassins. They're called hydroxyl radicals. These things are incredibly reactive, and this is the key part, they're non-selective. That means they'll attack and destroy just about any organic pollutant they bump into. They're not picky.
And today, we're zeroing in on one of the most promising AOPs out there, ozonation. This process basically harnesses the raw, destructive power of ozone, a molecule made of 3 oxygen atoms, to just obliterate those tough, persistent contaminants that other treatments leave behind.
Now this is where it gets really cool, chemically speaking. Ozone doesn't just have one way of attacking pollutants, it has 2, and one is way, way more devastating than the other. So first, you've got the direct attack. This is where the ozone molecule itself acts like a sniper, selectively targeting and breaking specific chemical bonds in a pollutant. It works, but it's kind of slow and precise. But the real magic? That happens with the indirect attack. This is where ozone helps create those hydroxyl radicals we were talking about, unleashing a fast, chaotic, and incredibly powerful cleanup crew.
This whole indirect pathway, it's a chain reaction. It's like tipping the first domino. It starts when ozone reacts with an initiator that's already in the water. This kicks off a huge cascade that rapidly generates a massive number of those hydroxyl radicals. You can really think of them as molecular piranhas. They just swarm through the water, tearing apart the complex structures of pollutants and making them totally harmless.
It's an unbelievably powerful process, right? But engineers and chemists, they're always asking, yeah, but can we make it even better? So let's take a look at how they're supercharging ozonation for maximum punch. Innovation here is really focused on 2 main fronts. First, there's catalytic ozonation. By adding a catalyst, think of it as a surface coated in metal oxides, we can dramatically speed up the process of turning ozone into those all-important hydroxyl radicals. Second, we've got hybrid systems. This is where you combine ozonation with other technologies, like electrocoagulation, which uses an electric current to make pollutants clump together. You put them together and you get this synergistic effect, where the result is way bigger than the sum of its parts.
And the results really show just how much better these supercharged systems are. Look at this chart. It shows the removal of something called chemical oxygen demand, or COD. That's just a key measure of water pollution. So on its own, electrocoagulation removed 69%. Not bad. But when you combine it into a hybrid system, that number skyrockets to an incredible 93%.
And we see that same incredible synergy right here, looking at total organic carbon, or TOC removal. Adsorption by itself gets rid of about 41%. Another AOP called Fenton oxidation gets 63%, but combine them, a whopping 91.4% removal. It is so clear that putting these technologies together creates a much more powerful solution.
But of course, none of this matters if your catalysts just fall apart after one use. For these advanced systems to work in the real world, at the scale of a whole city's wastewater plant, the catalysts don't just have to be effective, they have to be tough. They've got to be reusable.
Now, what's really fascinating about this slide is the proof of that durability. Here we see a standard manganese dioxide catalyst compared to a nano-engineered version. After 4 full cycles of treating wastewater, look, the standard catalyst performance starts to dip, but that nano-catalyst, it's still removing over 76% of the COD. It's a total workhorse. It maintains its high efficiency, proving it could actually be viable for large-scale applications.
So we know the technology can be made durable enough. Now let's zoom out to the big picture. We've got this incredibly powerful tool, but what are the trade-offs? What do we need to consider for the future of clean water?
Well, on one hand, the benefits are just undeniable. AOPs are super effective against the pollutants that conventional systems miss. They can disinfect the water, and they can even remove those dangerous antibiotic resistance genes. But on the other side of the coin, there are challenges. These systems cost more to run, they use more energy, and there's a risk of creating unintended toxic byproducts if you don't manage them perfectly. Plus, making these catalysts last a long time and be easy to recover is still a big area of research.
So ultimately, here's the bottom line. Advanced oxidation processes like ozonation, they aren't really meant to replace our current infrastructure completely. Instead, you should think of them as a vital, targeted upgrade. They're the specialized 4th stage, the final polish, that we need to add on to our existing systems to really tackle the invisible, complex pollutants of our modern world.
Which, of course, leaves us with one last really important question. We've developed these incredible tools to fight the invisible threats of today. But we live in a world where thousands of new chemicals are created every single year. The race between pollution and purification, it never truly ends. So how will we continue to innovate to protect our most vital resource?